action.
All right, so my project has been an experimental one. So it's been about generating turbulent shear in a water channel here at NTNU. So first of all, the main goal was to recreate results from a paper that my co-supervisor wrote, where he generated shear in a wind tunnel, but he sort of modulated the turbulence intensity. So this was sort of a big result, that you can have the same shear but different turbulence intensities. So my goal is just to do this, but in a water channel instead. So why would you want to do this? Well, generally you want to be able to recreate flows that you see in nature or in industry, right? So you can study them more closely. And particularly here at NTNU, it's actually related to the previous presentation. My main supervisor, Seaman, works on research in waterways with complex subsurface flow. It's the exact same phenomenon that was described earlier, so I won't go too deep into that, just for time issues. But yeah, so it's to sort of get this in the lab. And so the lab looks like this. This is the water channel. The water height is 0.8 meters, and the length is 11 meters. And the speed I run it at is around 0.3 meters per second at the center line. And the hydraulic diameter Reynolds number is around 300,000. So that's sort of to help you understand what's going on. And this is what you use to actually generate the shear and the turbulence. It's an active grid. It's basically a bunch of wings that you can sort of turn on rods. And if you turn them in the right patterns, you can make shear, you can make turbulence. You can make lots of things. And it's not, of course, it's not enough to just make the shear. You need to measure it as well. So I used LDV. LDV is a laser technique to measure flow velocity. I won't go too deep into that, but the main point is that it's non-intrusive, so it doesn't affect the flow. So yeah, this is what the grid looks like if you look at it sort of head-on. This is, right now, it's covering the flow completely. It's blocking completely. And if you open it up by turning all the rods, if this works. Oh, it's lagging a lot. So this, I don't think I'll be able to play the whole video, but I'll just click through it, I guess. This is what it looks like when you, I have to look at it from the side. Yeah, this is what it looks like from the side. This is it generating the shear. So you can see the rods sort of in the near the top are moving less, and the rods near the bottom are moving more. So that's sort of what's making the shear. You're changing how much you're blocking the flow in different places. And then, so in my project, I had 3 different modes: 15 degrees flapping, 35 degrees flapping, and 90 degrees flapping. It's a shame I couldn't show it at the right speed, but that's fine. So yeah, that's the shear, and then the turbulence, right? Again, this is a video. It's a bit harder to animate this, but what you're going to see is the vertical rods are going to be spinning at a sort of a random frequency while the horizontal ones are doing the shear. Again, it's hard to see, but they're turning slowly, and what's important is that they're turning randomly, but at around a certain speed. And these sequences for the turbulence were taken straight from research that my main supervisor did. I'll explain this right now. So the three turbulence modes I used were no added turbulence, just as a control, and then 1 hertz and 0.1 hertz random motion. And what's sort of interesting is that is the order of increasing turbulence. Slower motion in the rods causes more turbulence. It's still a new thing, so nobody has a good phenomenological sort of explanation for this, but this is at least the empirical truth. And what I plotted at the bottom, well, I haven't plotted this. This is also from my co-supervisor's paper. Is just sort of the angle over time of the turbulence rods. That's just to, like, the black line could be the 0.1 hertz mode, and the blue line, for example, could be the 1 hertz mode, just to sort of help you understand how they're moving. So yeah, where I did the measurements, I did them first of all at 35 mesh lengths downstream, and then at 95 mesh lengths downstream. So I did, at the first position, I did actually all of the modes, so all 9 combinations of all the modes. And then further downstream, I only did 3 just for time considerations. It takes a lot of time to do the measurements. So these are the results. Just to remind you what the goal was. The goal was to get this kind of same shear, but then different turbulence intensities, right? And for the 35 degrees mode, this is sort of the results. You get like you can see, the shear is linear, and it's sort of the same for all the cases, while the turbulence intensities are, different for all the cases. And also you can see that, if I can get the pointer up, let's see. All right, yeah, fine. So what you see is that, I'll go back one, that for the lower turbulence modes, it's more homogeneous than for the higher turbulence modes. I don't have a good explanation for that right now, but my hypothesis is that the higher turbulence modes cause more mixing, and then you get sort of more turbulence from the boundary layer up into the higher points of the flow. It's still a hypothesis. I have to look more at the data for that. And then this is the results for the plus minus 90 degrees flapping, so the mode with the most shear. Here you can see, again, all of the shears are pretty close to each other. But this time the turbulence intensities are not, the turbulence is not that homogeneous. And again, my hypothesis, and I'll consolidate that later, the hypothesis is that this is because of production of TKE, turbulence kinetic energy. And that comes from the gradient, and it comes from the mean velocity gradient. I'll consolidate that later. And this is just an example of the different shears you can make. And this is for one turbulence mode, but 3 different flapping modes, just so you can compare them on one plot. So go to the next one. These are the profiles further downstream, list a little less data. You can see that, again, they're very linear, and they're well maintained, except for the one with the highest turbulence. That's beginning to sort of even out. And again, I think that's because of the higher turbulence mode has more turbulent mixing, and then you sort of even out your flow. And again, the turbulence is not that homogeneous. Now, comparing between the different positions, just on the same plot, this is for the maximum shear mode, no added turbulence. You can see that the further downstream, you can see it more clearly here that it's sort of beginning to even out. It has a less of a gradient. And you can I've actually plotted the gradient itself here. This is just a very crude first order difference method, so this is only for indication, but you can see that you can see where the shear is highest and lowest. And actually really correlates really well with the turbulence intensity plot. And that really consolidates my hypothesis that this is because of the production term in the Rand's equations. So that's sort of all the results I had. And the conclusions are really that the shear is sufficiently linear for all the cases. I haven't shown you all of the data, but it's there. The shear slope control is sufficiently precise. Like, I can control how much shear there is by just changing the flapping angle, which you saw in that plot where I showed you. And the shear is maintained downstream, though it is a little less. I could even argue it's more linear downstream than upstream, but it's at least maintained. And also the turbulence intensity is controllable, independent of shear, but it is limited in homogeneity due to boundary layer effects, differential turbulence produced by the horizontal shear wings, because they're also making turbulence, right? And of course the lower ones are making, well, okay, I can't say that necessarily, but I have to check, but I would assume that they're making more turbulence. And lastly, of course, what I showed in the previous slide, the production of turbulence kinetic energy causes there to be a bulge in the turbulence intensity plots. So that's all my results, really. That's it.